In this lecture video, we'll learn about the two classes of substitution reactions and the reaction parameters that distinguish between them. We've already seen substitution reactions when we learned about the different classes of organic reactions. So remember that a substitution reaction is the reaction of a nucleophile that attacks an electrophilic carbon that bears a good leaving group. And often the leaving group we used was iodide or bromide, but we'll see in a bit that there are other good leaving groups for substitution reactions. There are two mechanistic components to this reaction. When we draw reaction arrows, we draw two arrows. One arrow shows the nucleophile attacking the electrophilic carbon, and the other shows the leaving group leaving to form an anion. And now the difference between our two classes of substitution reactions is the order that these two steps happen in. In an SN2 reaction, a substitution bimolecular, the two steps happen at the same time. In an SN1 reaction, a substitution unimolecular, the leaving group leaves first, and then in a second step, the nucleophile attacks the resulting carbocation. We'll look at both of these reactions in more detail now, starting with the SN2 reaction. An SN2 reaction is a bimolecular nucleophilic substitution reaction. And the bimolecular piece, or the 2 in SN2, refers to the rate-determining step that contains two molecules. That means that for a reaction like the one shown here, both the alkyl iodide and the hydroxide will be part of the rate-determining step. Remember again that our basic mechanism is one in which the nucleophile, here the hydroxide anion, will attack the electrophilic carbon of the alkyl iodide, and the iodide will leave. We'll look at this mechanism in more detail, and to do that I'm going to introduce stereochemistry at this chiral carbon. Now remember that when the nucleophile attacks, it attacks from the side opposite the leaving group. We call it a backside attack. And during that attack, as the carbon-oxygen bond begins to form, the carbon-iodide bond begins to break. So the transition state shows exactly that. It has a central carbon forming a bond with the OH group and breaking the bond with the iodine. So in this transition state, the central carbon, the electrophilic carbon, is essentially planar, or trigonal planar, and it's sp2 hybridized. There's two key features of this transition state. Okay, first, it's bimolecular, meaning it involves both the nucleophile and the electrophile. And the rate of the reaction is a function of both the nucleophile and the electrophile. Because the rate of the reaction is a function of both the nucleophile and the electrophile, increasing the concentration of either reactant will increase the rate of the reaction. Second, the stereochemistry at the electrophilic carbon, the one bearing the leaving group and the nucleophile, is inverted, meaning as the leaving group leaves, the nucleophile attacks from the other side, the backside attack, and that places the nucleophile in the opposite orientation from the leaving group. We call this stereoinversion. And in this example, the configuration of the alkyl iodide was R, and the configuration of the resulting alcohol is S. The absolute configuration won't always change, the R or the S, because that assignment depends on the priority rankings of the groups. But the nucleophile will always be on or bonded to the side opposite the leaving group, inverting the stereochemistry at that electrophilic carbon. And finally, because the reaction is concerted, meaning the bond breaking and forming steps happen at the same time in a single concerted reaction step, The reaction coordinate diagram will reflect that. The reaction begins with the reactants. The energy increases as they approach a single transition state, and then the energy of the system decreases as they move towards products. There are no intermediates in these reactions, and here the products are lower in energy than the starting materials, so the reaction is exergonic. Now let's look at the SN1 reaction, the unimolecular nucleophilic substitution reaction. And unimolecular here means that only one molecule participates in the rate determining step of the reaction. An SN1 reaction proceeds through two distinct reaction steps. And here I've just redrawn our starting material in a three-dimensional geometry so that we can more easily see what's happening. In the first step, the leaving group leaves to form a carbocation intermediate. Then in the next step, the nucleophile attacks the carbocation to form the new carbon nucleophile bond. There are two key aspects to note about this reaction mechanism. First, because there's an intermediate, and it's a carbocation intermediate, the reaction will form a mixture of enantiomers. Here the groups on the carbon are the same, but if they were different, if this was a chiral carbon, then the methoxide anion could attack from either face of the planar carbocation. It will attack both faces and equally, and will form a one-to-one mixture of enantiomers, or a racemic product mixture. Second, this first step, the leaving group leaving, is the slow step or rate determining step of the reaction. That means that the rate law has only the alkyl halide in it. It's unimolecular, and that means that only the alkyl halide will influence the reaction rate. The nucleophile has no effect on the rate of an SN1 reaction. And the unimolecular nature of the reaction is apparent again in the reaction coordinate diagram. The reaction begins with the reactants. The energy increases as they approach the first transition state, and then the energy decreases slightly as the intermediate forms. The energy then increases again as the second transition state is approached, and then the energy of the system decreases as it moves toward products. And of note here is that the second transition state is lower in energy than the first transition state. And that means that the first step of the reaction is the slow step, or the rate determining step of the reaction. Let's end this video with an example. Predict the major products of the SN1 reaction shown. The first step here is to identify the nucleophile, the electrophilic carbon, and the leaving group. And now because this is an SN1 reaction, I know it will proceed in two steps, with the carbocation forming first, and then the nucleophile attacking the carbocation. Because the reaction proceeds through a carbocation intermediate, and a carbocation is planar, the nucleophile can attack either face of the carbocation, and that leads to formation of two different enantiomeric intermediates. And these two intermediates will form two different enantiomeric products following deprotonation of the cationic OH2 group by base.